Okay, so let us start. I think after today's lecture, there is a 2-week break, 1 week of minor, and then 1 week of midterm break, and then the next lecture is when 8th, 9th, I don't remember, but sometime in the second week of March. Okay, so the exam is tomorrow. The room is 339, which is the exact room as practical. Okay, I'll send an email nonetheless, but I'm telling you it is in 4339, which is just beside my office, the place where the practical takes place. Okay, you are supposed to bring your laptop, and that's all. I mean, you can bring your pen and for doing some calculation, but it will be on Moodle. I have not made the question yet, so I'll make it after the lecture sometime today, tonight. But yeah, it will be a 20 minutes kind of exam, right? So that is kind of the idea. I will make it tonight, but tomorrow 8:30. So you should be there at least 8:20 or so. 4339 is the venue. Okay. Syllabus, whatever we do till today is the syllabus, as usual in IIT Delhi. That's the rule. So, so whatever we do till today is the syllabus. But okay. Okay. So with that, let us start the last lecture before minors. So till now, we have discussed primarily three generative models, or three family of generative models, if you like to say so. The first one was autoregressive generative model. The second one was variational autoencoder. The third one was flow based. And flow based and variational, both you can also think of as, not think of, they are latent variable models also. But if I have to pinpoint, maybe these are the three families that we have discussed in the lectures till now. Now, what is common between all of these three? Can you tell me? What is common between VAE, autoregressive, and flow? We try to train all of this. I mean, obviously, they're all generative models, but that is similarity between everything we'll cover. So that is not the answer, but uh, likelihood. So they are all trained based on likelihood or some upper bound, lower bound on likelihood. Autoregressive, you can directly evaluate the likelihood, so it is trained directly from likelihood. Same for flow-based models, you directly get the likelihood P of D given theta. Variational is tricky, you cannot evaluate the likelihood, it is intractable. So what you do is you find out D elbow, evidence lower bound, and based on that you solve the variational inference problem. But at the end of the day, you are trying to model these things based on likelihood of your generative model. That's what we are trying to do. So today we will try to move from likelihood based generative model to potentially something that is likelihood free. And that's the whole lecture for today. That's what we'll do. Okay, from likelihood based to likelihood free. So we'll basically be discussing why likelihood based is, what are the limitations of likelihood based, what is likelihood free, what do I mean when I say likelihood free, maybe surely discuss one generative model that is likelihood free, and that will be 1.5 hours. Okay. So with that background, let us start. So till now, as I said, we have discussed three models. The first one was autoregressive generative model. And keep in mind that each of these is a family. So there are many, like there is NAID, MAID, all of those in autoregressive. Even generative transformer is also autoregressive, right? Autoregressive generative model. The second one is uh, variational autoencoder, autoencoder, and the third one is flow based model. Okay, and as I was saying, these two at least comes under the idea of latent variable model. Although both are latent variable model, there is a subtle difference. In VAE, your Z is generally having lower dimension than X. That is always the case in VAE. Your Z is lower dimensional, your Z is lower dimensional than X. Generally, you can take high, but generally it's lower. But in flow-based models, your Z and X are having same dimension. Z is not low dimensional as compared to X. Z and X are having same dimension. Even when we were doing that MAAF and IAF, they were having actually same dimension. I was sampling one at a time, but actually if there is x1, x2, xk, it is z1, z2, zk. It cannot be that x is up to k and z is up to m. That will not happen. So flow-based model, that is actually a restriction where, there your dimension of your latent variable is same as the dimension of your original data that you want to generate. So naturally, that means a certain number of, the parameters will be little bit more because input dimension has increased. Okay, so keep that in mind. That is one difference between VAE and flow-based model. So yesterday, I think you were asking, someone was asking that is flow-based model better than VAE in all aspects? This is one aspect, for example, where you can imagine that VAE is better actually. That you have flexibility of selecting the dimension of Z, the latent dimension. You do not have that in case of flow-based model. Yeah. Correct. Correct. No, autoregressive model as a flow-based model, we are talking about flow-based model, but inside flow-based model, we are saying that we can imagine a autoregressive kind of structure that is transforming one distribution to another. And that we did by introducing Z only. So Z was there and it was having same dimension, right? We also said that even in variational, it was probability of x or y given x or x given z was Gaussian, right? I also said that can also be autoregressive. So initially I said that can be mixture of Gaussian, x given z. We take it x given z to be Gaussian because that is, in most cases, that suffices. Does not mean that it will suffice in all cases. And definitely does not mean that you should always take it to be Gaussian. The vanilla variational autoencoder take or assumes it to be Gaussian. Probability of x given z. Right? So that was one consideration also. So yeah, you can always mix things up and still they will be valid generative models. Okay, but all of these are dependent on likelihood to be. For training this model, we rely on likelihood, right? So all the three family of models rely on likelihood, log likelihood. Elbow is again over likelihood, so it relies on this. And we know that we use likelihood because we know that the perfect model will have the highest likelihood. The perfect model that we can have will always have the maximum possible likelihood. That's the whole principle of maximum likelihood estimation. Obviously, under certain assumptions and no noise and all of those things, but it will have, right? But that does not mean that if I have two models, let's call it model M1 and model M2. So if model M1 is having higher likelihood than model M2, that need not necessarily mean that the samples generated from M1 will be better than samples generated from M2. It need not be the case. And you know about examples where it happens. The example is memorization. What will happen if your model start memorizing? It will generate the same data as the training data, which means it has not actually learned the distribution, correct? And you are not actually getting diverse set of samples. Yeah. You are training, I'm talking about during training, right? Yes, so that is the whole problem. So suppose you are training the model based on likelihood and you get a model which is based in the training data. It does not mean that during test that model will have the higher likelihood. Correct. Correct. Even in that case, memorization will not solve that problem. Memorization, the data is from your training data itself. That's what it is generating. So the likelihood will be high. But that does not mean it is a good model. That you are getting the data which looks very realistic because those are real data. But then what is the purpose if I have to just repeat those data? So in that case also it will fail. I mean, you are trying to learn the sample, right? Distribution. So some of the samples you keep aside, you learn the distribution, and assuming you can evaluate the likelihood of the distribution, which might not always be possible, but assuming that, you put this test data and try to see what is the likelihood of that, right? And the easiest example of that it does not work is actually mixture of Gaussian. What will happen? Think about it. So, okay, let me first write the actual statement. The actual statement was the perfect model has the highest likelihood. However, this does not mean a model with higher likelihood is better. And when I say better, it means in terms of samples. And the easiest example for this is actually you take this distribution, right? Mixture of Gaussian. So this is my actual distribution. Okay. Now you assume that you variational. So you assume you have a Gaussian, and you maximize the likelihood of that Gaussian so that that distribution best represents data generated from this distribution. Yeah. Yes, more or less. Yeah, I cannot think of any scenario where you cannot. Right. I mean, you can imagine a one side skewed or something like that. That will be multiple Gaussian sitting within that single Gaussian one peak. And so that will make it skewed. Okay. So yeah, it can theoretically model almost everything. Correct. But you will not know that. I mean, in this case, you do not know this distribution. I have a mixture of Gaussian, I have data from that. So when I have data, I do not know it is mixture. If I plot that data, I can maybe have, okay, maybe all the data are from one mode. Maybe there are three modes, data are from two modes. So you might not have that information at all. This is a empirical distribution which I do not know. And I have samples from that. Because if I know this, then I don't need generative model, right? So I have sample from a multimodal Gaussian, just assume it, right? And now the whole idea of generative model in general, if you think about it, is that you assume a model family. When you are taking autoregressive, it's a family. Autoregressive have certain limitations and you are working with that limitation, like the Gaussian assumption and whatever, right? When you assume VAE, it's a family. VAE also has certain assumptions and you are working with that. And similarly, even if you take flow-based model, which probably has no assumption as such, But even in that case, your optimization is an approximation, and you have to live with it. You will get the local optima, not the global optima, and that you cannot do anything about, right? So no matter what model family you are taking, you are not getting the optimal one, unless and until you are very lucky, and that luck will be in 1 in a million case maybe, and even in that case, that will never happen in your lifetime, right? So what you are always doing, you have data from some unknown distribution, you are assuming a model family. That model family is autoregressive, that model family can be VAE, that model family can be flow, it can be something else also, diffusion, whatever, right? And then you are trying to tune the parameters of that model family so that that model best represents the data you have. Correct? Everyone agrees? That's what we are doing if you think closely. So if that is what we are doing, in this case, assume that I have, because this is easy to visualize, I have a mixture of Gaussian and I have samples from that mixture of Gaussian, right? And now I assume that my model family is Gaussian because I do not know this. So if I take the model family to be Gaussian and maximize the likelihood of that, what will I get? What I will get is something like this. The forward KL divergence is what we will get. So we'll get probably something like this is what we'll get. This will be the distribution that will have the maximum likelihood. Because with Gaussian, you have taken Gaussian already, and maximizing likelihood, we know that that is equivalent to minimizing the forward KL divergence. We saw that I think in flow matching, not flow matching, flow based model, we did that actually. Where we started with the two views, one was the forward KL divergence, the other one was likelihood, and we saw that we both are coming to be identical. So last to last lecture, we did that. So if you do that, this is what you will get. Now, is this a good model? Because this is having the maximum likelihood. Some will argue probably if it was the reverse one, if we get that one, say one mode is captured, that is perhaps much better. Most will argue that, right? Because in this case, you can imagine that if the modes are well separated, you will perhaps get a distribution where, even in this case, right? See, think about the modes. In the real distribution, where most samples will lie? Near the two peaks. In the variational, where most samples will lie? In the middle, where actually no samples would lie, almost no samples would lie. So you can understand what can happen in a likelihood, given that we are working with an assumed approximate model family. We are restricted to that, right? Our model family is not perfect. There are assumptions embedded in our model family. Autoregressive, we assume Gaussian and only the mean and covariance change and all of those things, right? So that is the problem. Okay. And then memorization is another problem. Overfitting can be another problem. But I'm not saying all of this problem will be solved by removing likelihood, but likelihood is not perfect. That's the message I'm trying to give. Okay. Don't expect that if I go to likelihood free, everything will be solved and I will get some magic thing. It will not happen. But likelihood is not perfect. So there is, there is definitely a reason for exploring alternative things. That's the basic message. Okay. There are some. Likelihood can be one. For example, again, KL divergence can be one if you can compute it based on data, right? Diversity can be another metric, that how diverse is it. But there is no one metric that will tell you everything. It depends what you want to capture. So the based on that, because diversity will not tell you diversity, right? So what you want to capture is perhaps what you should be looking at. Okay. So, and also obviously one more reason for exploring likelihood free is that we know VAE, in VAE, we cannot evaluate the likelihood in the first place. We are doing an approximation of likelihood. So that is itself, it should be enough to evaluate framework that is likelihood free, right? So because of this reason, we asked the question, or people asked the question, right, 10 years ago, can we comment on similarity of two distributions based on samples. Can we comment on similarity of two distributions based on samples? Samples available from both the distributions. So mathematically, if you have to write it, mathematically it means suppose we have, we have, let's say S1, which is basically X sample from, let's write P, okay, where P is some distribution, okay. So X are set of samples, so S1 is set, first set, so set of samples where all the samples are sampled from some PDF P, and similarly, and S2 where we also have samples X, I mean I can write X hat also, that's okay, but because I'm writing the sample, it's okay, from Q, okay. So I have a set S1 where I have samples, let's say n number of samples, and those samples are from some PDF P. Similarly, I have a set S2 where also I have samples, and those samples are from another distribution Q. I do not know P, I do not know Q. All I know is these two sets S1 and S2. Can we comment on similarity of P and Q based on these sets S1 and S2? Because if I do not know P, I do not know Q, that means I definitely do not know the likelihood. So likelihood computation is now out of the picture. So can I comment on this P and Q similarity between them or difference between them based on only these samples? That is the question we are asking, because this is what you have to answer if you have to go likelihood free. We have to make some commentary about the distribution based on the samples, because at the end of the day, it is distribution which you want to match. So even without computing the likelihood, this will be some distance metric between the two distributions. It need not be likelihood, it need not be KL, but some distance metric between the two distributions that we will like to minimize, right? So it has to be that. So can we, so that on that context, can we do this? Because if you can do this, can we not take it and do the same thing, right? So where we have these things, right? So can we go, and then from here actually this question comes. I'm not writing it again, but from here I'm asking the question that can we now comment on similarity of P and Q based on set S1 and S2? If I formalize that question, that's what we are asking, right? So if that is what we are asking, uh, obviously we are talking about sample testing. There is something known as two sample test. The idea of two sample test is that you have two sets of sample. You can come up with a null hypothesis that these two sets are from the same distribution, which means P equal to Q. And accordingly, we will also have an alternative hypothesis, which is P is not equal to Q. And then you can come up with some statistics defined in terms of these samples. And if this that statistics, which is some distance, is less than some threshold, then we can say, okay, they are similar. If that statistics is greater than some threshold, we say that they are not similar, they are different. Clear what I said? I'll anyways write it, but I'll repeat once more before I write it down. What we can do in this two sample test is that we can define a null hypothesis. A null hypothesis is the positive one, so P is equal to Q. The alternative hypothesis is P is not equal to Q, right? Now with this, we can define a metric, some distance, something like that, right? And that may not be unique. I mean, you can come up with your own metric there. But those metrics is calculated based on this set S1 and S2, which means samples. And then if that metric, if it is distance, then if it is less than some threshold, it cannot be zero, obviously. Even if they are from same, this because you are drawing samples, they are random, it will not be zero. But if it is less than some threshold, you can say that because it is less than threshold, they are almost same. The null hypothesis is correct, you can accept it. And if it is greater than, you can reject the null hypothesis, which means the alternative hypothesis gets accepted, and then they are not. Okay. So that is the whole idea. So let me now write it down. So we can use two sample test. Okay, we can use two sample test. The idea of two sample test is that you have a null hypothesis, which we denote as H naught, which says that P is equal to Q, which means both these sets, the samples have come from the same distribution. That's what it fundamentally means. And then you also have alternative hypothesis, which naturally is P is not equal to Q. Okay. And then you define you cannot. It's a personal choice. Let's put it that way. So as a decision maker, you have to decide that, and that can vary. It depends on how confident you are, how many samples you have. It will functions of all that. So there is no one way of doing it. Okay. So you define we define T. Let's say T is that statistics, right? So T, and there can be, as I said, there can be many ways of defining T. Let me define just one way, and but that is not the only way. Let's put it that way. 1 by cardinality of S1 x belonging to S1 x minus 1 by cardinality of S2 x belongs to S2 x. What is it saying? If the mean matches, which is the not a good metric, but anyways, the mean matches, and matching means again less than a threshold. So if the difference of mean is within some threshold, we can say that the distributions are same, right? Now you can say why mean? No, it need not be mean. You can take both mean and variance. If the mean and variance matches, then the distributions are same. You can say no, why move both? Why only two? Take 5, take 10. It's your decision basically what to take. You will decide that. You will decide the threshold. You will decide what to match, and based on that, you will try to come up with. So this T has to be decided by you, and it can be decided based on problem at hand. For example, if you know both are Gaussian, both are having same variance, then only match the mean. You know that, right? But you will never know that probably. You might know it in certain cases. For example, where do you know it? The only case I can imagine is suppose someone is supplying steel to me, steel rod, reinforcement bar. If it is reinforcement bar, they always say in manufacturing wise there is some 5% variation. That means your standard deviation becomes something of that 5% range, right? 5% is COV, so you can find your standard deviation. So now if you have to do, you know that both are still. So both will be different because of, let's say, law of large numbers. So both are Gaussian, let's say. Both are having 5% variability. You only match the mean. So in that case, it might work. But in most cases, only matching mean is not a good idea. I think I don't need to explain that why matching only mean is not a good idea. Right? And that's why you can also decide to match variance, you can decide to match higher order moments also, and all of that is possible. This is one way in which you can do it. However, this is problematic. One is how many moments. Second one is the statistics do not really mean much mean and variance, these things, when you go to high dimension. In high dimension, maybe you need to match the first 200 moments. I don't know. I'm coming up with this. I'm cooking this number 200. It can be 1000 also. It can be 100 also. But you need to match very high number of moments, which then becomes very problematic, right? So this kind of metric we need to define, but this matching of moments is perhaps not a good idea, particularly in generative modeling, where our images are, the time series are, or our data set is always high dimensional. I mean, the lowest you will work with is in 1000. The highest you will work with is, I don't know, million, maybe even more. No, because that n has to be, if n tends to infinite, then yes. 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 If n tends to infinite, that means you are matching the two distributions. That's what it means. But you cannot match. In n tends to infinite moments, you cannot match. So that you will not be able to do, but theoretically, if you match all the moments, that means the distributions will match. That's what it means. Okay. Yeah. Not exactly. So this is like null is defined on some hypothetical distribution from which the samples are generated. Yes, yes, yes. Because the checking is on with respect to samples, so you cannot have that P and Q. Okay. So this is one moment. You can decide to match second moment, third moment, fourth moment. All the best if you try to match 100 moment. I will not try that, but you can try if you have enough time and nothing to do. Try it on a weekend. Okay. But I'm not trying that, right? And anyways, that is problematic, particularly in high dimension. So in high dimension, that is really problematic. But even in low dimension, let me give you examples where matching only mean can be problematic. So let me give you examples. For example, if you are only matching mean, you can, and your distribution is Gaussian, and you are only matching mean, you can always have a scenario where your original distribution is this and you are getting this. It is always possible, right? If you only match mean. Now assume the scenario where you know your distribution is unimodal. You know that. And you are matching the first two moment. Even in that case, it is problematic. So let me give you an example. So let's say your distribution is unimodal. I did not say it is Gaussian. Let's say it is Laplace distribution. So Laplace distribution is something like very sharp distribution you get, right? Almost discontinuity. Because modulus is there, so it is there. And if you do a Gaussian, what will you get? I mean, ultimately it has to be one, integrate out. So the diagram might not be correct, but you can, the message is clear, I guess, that you can never match a Laplace with a Gaussian. So you cannot do that, right? So even if they are symmetric, both are symmetric, both are having the same mean, both are having the same variance, you will end up with something like this. So clearly not a great idea. So what can we do? Can we do something? Two, can we somehow come up with some good tea? Now this is a course on machine learning. I mean, deep generative model, but also machine learning, right? In machine learning, whenever you don't know something, what do? You try to learn it. So can we learn somehow a model that will help me do this thing? If, so the question is, can we learn a machine, or can we have a machine learning model that will do this task for me? We can always ask that question, right? So what is this problem? What kind of machine learning problem it is? You know, classification. You're trying to understand if samples are from one distribution, which is P, or it is from the second distribution Q. So it's a binary classification problem. Correct? So can I not design a classifier that will take my data X and tell me whether it belongs to class A, which is P following distribution P, or class B, which is following distribution Q. You have some question? Yeah, you can do that. Yes. Because it's classifier. So yes. Okay. So the question or the rather the solution, one solution is that we can always design a classifier and let it be neural network based classifier, right? Uh, which will a classifier which will kind of classify each data point which class it belongs to. And so it will basically give you that, okay, it belongs to this class with this much probability, this with this much probability. You can choose a threshold, and based on that, you can always say that where that sample belongs. Correct? So one option is to design or have whatever you like a binary classifier. Right? One option is to have a binary classifier. And let's give it some name. It's a neural network for now and for this course. Let's say it is D5. The classifier is a model. I mean, that model we are calling it D. And because it is a model, a neural network, it will be parameterized by some weights and biases. We are calling that phi. So it's a some nonlinear function D and phi. The last layer will be sigmoid because binary classification. The intermediate layers can be any activation function you like. Right? So D of phi, it will take X or it will map X. X is the data I have, image, time series, whatever data I have. It will take a data and it will tell which class it belongs to. And C has two options in our case, one is P, other is Q. So these are the options that C has. These are the options that C has. Binary classification, right? It is complete set. I am showing X as a not a sample, but like it can be any sample. I am showing just one sample. So it can be all set. It can be all because so let's say X. I don't know whether it is from S1 or S2. So the classifier will try to say that whether it is from S1 or S2. If it is from S1, then P, S2, then Q. And it can be for any sample. It's not one sample. But when you model it, it's a X becomes a variable. So X here is a variable. For that, you can have as many samples as you want. Correct? Correct. It also will have. It also will have. It also will have multiple samples. I'm just showing one sample. Not necessarily, but yeah. I mean, you will ultimately, when you compute the statistics, when you compute the loss, right, of the classifier loss is not based on one sample. When you train the model, during prediction, you are right, it will have one sample, but during training this model, you will not have one sample. You will have multiple samples, right? Similarly, you can have multiple samples given to it. It is able to cluster or classify the samples. During training, I will come to you, I've seen it. Okay. So during training, you can give, you have to give all the samples. So it will, the model will learn based on that, and it will then try to classify any given sample into P or Q. It is same as before because remember, you have two sets, right? One is your S1 where you have samples from P. The other one is your S2 where you have sample from Q. That is what you have. Now imagine I have a new sample that is coming. Should that go to S1 or S2? That's also a question, right? The same flavor. Now, when I go to the second question, that's what I have shown here. I have a new question, new x. Now, should it go to S1 set or S2 set? I can only do that. How will you do that if you know P and Q? For that new sample, you will put it into P, put it into Q, evaluate the likelihood. You will see which likelihood is more. You will say it belongs to that. Is that not what we were doing? But now I do not know P and Q, but I want to evaluate the likelihood of that, or evaluate some metric for that which will allow me to distinguish. See, that is what it is doing, right? Correct. Let's put it that way. Hmm. Correct. Correct. That's a valid problem, and we'll come to that maybe towards the end of today's lecture. But that's a valid problem. Often we try to make this D a simpler model. We try that. Okay. And what is D? If you have some background on where I'm going, you will probably have guessed that. Okay. So yes, we try to make D simpler, but that not in this context, but in the broader context which I have not yet reached. So your point is actually correct, but we'll reach there maybe in some time. Okay. So we can try to do that. Now, how do you train a classifier? Any idea? Binary cross entropy? How many of you know about binary cross entropy? I see many people do not know, so let me derive that. It will take two lines, right? I mean, those who know it, they know that it will take two sentences. So, okay, what is the likelihood of this? We are doing a binary classification. What is the likelihood? Bernoulli distribution. Whenever it is 0 or 1, it is always Bernoulli. You can assume that P to be 1, Q to be 0, so then it becomes a Bernoulli distribution, right? So for this case, the likelihood is probability of D. This D is not your discriminator, or the classifier. This is your data. I've written D already, so don't get confused. D given phi. Okay. This is equal to product of all the data points you have, I equal to 1 to n. I'm assuming n data points. Probability of Ci, where Ci is the class. C, this is C, not X. Okay. Given Xi, comma phi. And now this distribution is actually Bernoulli because C is either 0 or 1. So it's Bernoulli. So this is equal to product over I, Bernoulli Pi, which is your class, given, here comes your classifier d phi of xi. So basically the classifier gives you probability of success and failure. I mean, one is enough, the other one will be 1 minus. That's what it gives you. Probability that it will be 1, and that naturally means 1 minus that of will be. And now, if that is the case, let me write one more equation. So this is equal to, what is the Bernoulli PMF? Can someone tell me? P. What is P here? D phi xi power Ci multiplied by d phi xi power 1 minus Ci. Right? This is the PMF of Bernoulli. Now we do not work with product, we work with log. I mean, so that will make it the product as sum. So which implies log of P d given P is equal to, if I take log, log, it will become summation over I Ci d phi xi plus summation over I 1 minus Ci log is there, correct, thank you, and then log of 1 minus d phi xi, right? Now what is Ci and what is 1 minus Ci? The number of success and number of failures, right? So if I draw samples from, let's say, P or the data, that is like getting number of success, and if I draw from failure, it is like getting number of failure, which is 1 minus P, which will be basically Q. So this is equal to expectation x being drawn from P Ci. I've assumed P to be success and Q to be failure. So in that sense, it is coming. Okay. Not Ci now. It will. C is not there actually. C is already here. It will be log of d phi x plus expectation of failure. I mean, with respect to 1 minus log of 1 minus, right? Log of 1 minus d phi x. Okay. And this is actually equal to, now it will start making sense, 1 by S1. S1 was from P, right? Summation x belongs to S1 log of d phi x plus 1 by x belongs to S2 log of 1 minus d phi x. That's all that it means. Okay, and then if I take a negative sign of that, that's the binary cross entropy. So this one is the likelihood. I should maximize it. Where is the sound coming from? Inside or outside? Outside, right? Then please close that door. Come on. Thank you. Yeah. So this is your basically likelihood. This is the likelihood, and likelihood we like to maximize, which means negative of this I will like to minimize, and the negative of this is actually binary cross entropy. This is your Bernoulli likelihood. Okay. So that means how will I find out phi? So this means finding phi. So phi star is equal to arg max phi, and let's give it a name. I have not given a name, right? Let's call it V. Okay, this thing. So this whole thing, or maybe the one above. Okay, maybe this one. This one. Let's give it the name V of P comma Q. You can write. Okay, for now. Well, I'll change it, but for now you can write it V of P comma Q. Yeah, and phi. Yeah. Oh, that is very simple. So what is CI? Probability of success, right? That is how many times you will get from the first one. And what is 1 minus CI? It can either be 1 or 0, but there is a summation over that. So what does it mean? What does it 1 mean? 1 means you are getting the first sample. So that means the probability of getting 1 is the first one. And similarly, 1 minus CI means 1 minus 1, which is 0. So that means getting from Q. So failure, basically. Where is that? Did it go? Here. So CI means, we think about, we did it earlier also. Remember that dice throwing example we did earlier? We said that this first term will become number of head, the second term will become number of tail, and then we derived that probability of getting head is equal to nh by nh plus nt. That same thing is happening here. So nh is number of head, which means nh is probability of, I mean, how many times you can get from the first set. Nt is from the second set. So it is like integration of fx gx dx. In this case, it is not integration, it is summation. So that's what it is. Okay, and that will become even more clear when you go to this, the approximate expression. What is the approximate expression saying? How many times you will get, the number of times you will get from S1, right? Now, what is the chance you will get from S1 when you have S1 plus S2? Cardinality of S1 divided by cardinality of S1 plus cardinality of S2, right? See, this expression will give you exactly this one only, because in summation form. I just brought the expectation because I want you to know the expectation form, because that's what we will be using. Yeah, only then the first term will survive. If everything will get 0, it will not survive. Yes. Yes, because 1 by S1 is that, because 1 by Si will go inside, right? 1 by S1 is the number of times you get. So because of that, because that's the probability. Which one? Mm, uh, I don't think they are. Hmm. Hmm. That will be 10. No, 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 no. So when you're doing 1 by S1, right? See, in this case, what will you get? 10 times log of d5. Where is that 1 by 10 come from? Here, where is that 1 by 10? Where is the 10? The 10 is missing, right? If you don't, if you remove 1 by S1, the 10 is missing. In this case, you are getting 10 times log of d. If you remove that S, you will get log of d. Correct? Yeah, 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 yeah. No, no, you will not get, because xi is changing. So your term inside is not same. It's ci. What you are saying is correct. If it's a plus a, it is 2a, but it is not a plus a, it is a plus b. So that ci, what you are saying is correct. That is only when that other term is constant, right? But let me check it. Okay, I'll check it. I'll confirm. Okay. Yeah. So I'll check it. Okay. Anyways, so we'll check it. I understand what you are saying, but let me check it. Okay. Uh, so anyways, if you have to find it out, you will just do, V of P comma Q, and obviously semicolon phi, but that I'm not writing. Okay, here this is obvious, right? This is how you generally train a classifier, correct? This is how you train a classifier. But now the question is, how can I use, or how can we use this concept to develop a generative model? Because this has nothing to do with generative model yet. This is just the classifier we have trained and nothing else. How can we use this to train a generative model? Any ideas? How can you do that? How can we use this concept within the training framework of generative model? So basically, any generative model you take, it's your choice. It can be a VAE, whatever you want to take. Okay, it need not be a VAE, but it can be any model you take. For training that model, instead of the likelihood maximization, that generative model will generate samples that will come from that some distribution. You have samples that are coming from the true distribution because you have training samples. And based on these two samples, you will now try to classify it, that whether the generative sample belongs to one or the other. So we can use this classifier as an alternative to the likelihood. Because generally, how do we train a generative model? We have the generative model, it generates data, we compute the likelihood of the data and try to maximize it. That's what we do. Here, what we will do is, we will have a generative model, it will generate data, but we will not try to compute or even maximize or anything of the likelihood. We will now bring this classifier into picture, and this classifier will tell me whether the generated data is now belonging to the true data class or something else. So fundamentally, to train this model, we build on what is known as a game theoretic approach, where you have a generator now which is generating model data, and it's a game now between the generator and the classifier, right? Any question? So the idea is, no, let us wait. Okay. So the idea is to develop a generative model we rely on a game theoretic approach. To train this model, we rely on a game theoretic approach, where the idea is that one model, which is a generative model, because generative we call it G theta, generates X. So basically, G theta is there, it will take Z and transform it to X, and not only that, this X is now from P of theta of X. If we take, yeah, you can combine it, but yeah, you don't need it. Yeah. Okay. I mean, you can always generate refine VAE further with this, but yeah, I mean, you can, it can be anything. There is no restriction. This Z can be low dimensional than X. Z can be high dimensional than X. Z can be of same dimension than X. Z to X, that mapping can be a generic neural network. It need not be invertible. So all of those restrictions are now lifted. So there is no restriction. It's just a model. We don't want it to be invertible. We don't need it to be invertible now. So one model G theta that maps from Z to X and it follows P theta, right? The other one classifier D of theta, D of phi, uh, tries to classify, distinguish, whatever you call it, distinguish X from P theta of X from uh, X from P data of X. What is P theta? The true distribution that we want to learn. What is P theta? The distribution that we are somehow learning, right? So what the classifier is trying to do? It is trying to say that it will try to classify when you're training this model. It will try to classify that whatever data you are getting, that is getting generated, that should not be classified as true data, right? And then it's a game then between the two. Why is it a game? Because the generator G theta is trying to generate data, and it will try to generate data such that the generated data, because it's a generative model, is as close as possible to the true data in the statistical sense. So the generated data, it will try to generate data from P of data. It will try to make P theta close to P data without knowing anything. That's what the generator will try to do. Correct? What the discriminator, so now I'm coming to the name, although I may said it once by mistake. So what the discriminator or the classifier will do is that it will try to discriminate the two things. It will try to identify what is generated from the model and what is the true data. So basically, the generative model, the generator, is trying to fool the discriminator into believing that the data it is generating is true data. And the discriminator is trying to catch the generator, that it is trying to fool me, I will not allow it to fool me. So it's a game between the generator and the discriminator, and that's why I use the term game theoretic approach. Right? Clear? Any question? It can be anything. Anything. Autoencoder is one example I give, but it can be anything. Z is the latent variable. So it is also a latent variable model. Okay. So Z can, it can be any model. Autoencoder example I gave because you know that, but it need not be autoencoder. It can be any model you like. Okay. Right now nothing is trained. I've not even told you how to train it. I've just told you two things, that the generator will try to generate data so that the classifier is not able to distinguish those data from the actual data. The generator will try to generate data such that the generated data looks like real data to the discriminator, the classifier. That is coming, because the goal of the discriminator is itself that it should try to discriminate the two things. Right now nothing is trained, so that is the invalid point. All of this will come when I've trained. Did I say that the discriminator is trained? I did not say that. That's why point is not valid. Okay. Have we trained the discriminator yet? We have not trained it yet. Phi you do not know. I told you how to train a classifier, but I did not tell that that has already been trained. So that model is not yet trained. So you do. How do you know how will it get trained? How do you know? Do you know how will it get trained? No, it has to be trained together. So we have not yet discussed that. That's the whole point, right? So wait for 5 minutes. We're coming to that. Okay. So why will it not be able to classify? Because first of all, we have not yet trained it. So what that comment is itself invalid. But for just for the sake of discussion, why will it not be able to classify? Neural network is a universal approximator. So why is it that it will not be able to classify? It has hidden layers, so it can, even if they are not classifiable to human eye, it can take it to the latent space. So why will it not be? Any specific reason it will not be able to? There is no reason it will not be able to, in theory. Okay. Okay. So this is the game theoretic approach, but then theta is unknown, phi is unknown. How do we train the model? So training the model is actually dependent on this philosophy only, this theory only. That what is the generator trying to do? It is trying to fool the discriminator. What does fooling the discriminator means? The discriminator should not be able to classify, right? So if the discriminator is not able to classify, then what should happen to this likelihood? When the discriminator is able to classify, what happens to this likelihood? Is maximized. If you want the model should not be able to classify, what should the generator do? Minimize. That means you will train the theta so that this likelihood is minimized. Correct? But a discriminator, what it should be able to do? Classify. So that should maximize this. So this same loss function should maximize with respect to phi, but minimize with respect to theta. So it's a max min optimization problem. And both of these are done together. So because it is done together, so there is no pre-trained model that it is not able to classify, that question will not come. And there is no generative model that, because that's not yet trained, that not being able to generate will also not come. Yes, a question will come which he raised long back, but that I'll come in another 5 minutes. So let me repeat. The generator will try to generate data that seems to the discriminator that it is coming from actual data, which means the generator is trying to fool the discriminator. Fooling the discriminator means it is not able to classify. Not being able to classify means the loss, or in this case the likelihood, which was supposed to be maximized, should now be minimized. So when you are training the generator, this should be minimized. But when you are training the discriminator, then what should happen? This should be maximized. So generator training, minimization; discriminator training, maximization. Okay. So therefore, therefore, uh, theta star comma phi star is equal to arg mean, so minimization with respect to theta, arg max with respect to phi, v, and now I'll write it as function of theta and phi. Right? And now comes the bottleneck. So what was being mentioned earlier, that if the discriminator is too strong, even if there is small discrepancy, it will start saying that even if the data is actually coming from the same distribution, it will say no, it is from different distribution. So you generally do not want to make the discriminator too strong. Also, because both of these are training together, at least in alternative epoch or something like that, this training is highly unstable. Training And by the way, this model is known as, I did not say the name of the model, it is known as Generative Adversarial Network, or GAN. This model is known as Generative Adversarial Network. Generative, it is generative. Adversarial, because there are two adversary here who are in a game. Network, and that's okay. This is called Generative Adversarial Network, or GAN. Okay. GAN is likelihood free, but training GAN is notoriously difficult. You have to use all the tricks that you can have, and even then you might not succeed. What are the few tricks that are used? For example, one I said that you make the discriminator intentionally weak. That is an obvious trick people use. The second trick that people use is that you train the generator for 5 epoch, discriminator for 1 epoch. So you do that scheduling kind of thing, that how many epochs this will be trained, that will be trained. And 5 and 1 is not some magic number. It can be 3 and 1, 5 and 2, I don't know that number. That is very problem dependent. If you make it 2 week, it's a problem. Then it is saying everything is same. Then it's so it's unstable. That's why I say the training is unstable. So it is definitely a problem. I mean, even what does equal mean in this case? You have not even trained your model, so you don't even know what does equal mean. I mean, the notion of equal is not clear because both are doing different tasks. You will say, okay, number of layers will be same, but the classification is an easier task than generating of data. So why should they have equal layer? If they have equal layer, then actually the discriminator is very strong. So it's very problem dependent, right? It's very problem dependent. So you will not be able to tell uh, one way or the other what is happening, right? You will not be able to tell. Okay. In the problem statement, no. In general, I mean, what we'll do first, it doesn't matter. Mean max or max mean will not matter. As long as max is over phi and mean is over theta, it's fine. Because anyways, you will initialize both theta and phi and then start doing it. But yeah, it might matter that maybe, I mean, so theoretically it does not matter what I mean. Practically it might, because maybe learning the phi for once gives you a very good theta in the next iteration and it starts converging quickly. So in that sense, yes, but generally no. Okay, but theoretically no. No, it is not used nowadays. It is the use has reduced now. It is used because it could generate data. When it works like magic, or it was working like magic at least. So people are, and this idea is very attractive, right? That there are two players who are playing game and in the process generating data. That idea itself is very attractive. So, and then again, people are also working on it because remember, when you say people are working, they are working in the research setting, right? The research environment, when something is not working, to make it work itself is a research problem. So people tend to work more in areas that actually do not work. At least many people do that, right? That this is not working, so that's a research problem for me. So when it's a research problem, you will improve upon it. When you improve upon it, that helps. So even in that case, um, so yeah, but now not many use GAN or VAE. It is also true, at least in domain where machine learning has infiltrated quite a bit, but people used to use it a lot. Okay, so what are the limitations again? Unstable training and mode collapse. Mode collapse I did not talk about, but mode collapse is like if your data is having multiple modes, it is just generating data from one mode. And that is again related. So whatever I'm saying, the limitations, they are all related to unstable training. The training is notoriously difficult because you are training two networks, min max is anyways difficult, and all of that. Okay. Repeat once. Yeah, yeah. So that's why there have been. I mean, I'm not talking it today, but there are different variants of GAN also. And there, people have come up with different laws between Wasserstein distance, and all of those things have come. So all of those has come because this loss is anyways a very difficult loss. So binary cross entropy is not a good loss. So that is also a reason. So there have been cases where people have tried modifying the laws and all of those things. So that has also been attempted. So That period that he was talking about, right? When people were working on GAN, these are the things they were doing. They were coming up with new loss metric. They were coming up with new ways of training, new scheduling, some warm start or something like that, and all of that were being tried. And still, it is very difficult. Okay, and mode collapse is a very genuine problem in this case. Any question? Unstable training. Once it reaches one mode is where it's a local optima, right? So then it will not try to go out. It becomes very difficult to make it go out. Yes, but the other models training is not having theta and phi. It's not min max. In that, mode collapse happens in other models also, but it is more prominent in GAN. I'm not saying other models do not have mode collapse. All generative models have mode collapse, but it is prominent in GAN. Okay. Good. I'm coming to that. That's a good question. I'm coming to that. So actually, that is written here only. The expectation. Look at the two expectation. What is it with respect to P and Q? In your case, P will become P theta, and Q will become P of theta. So that's how. In fact, that becomes the second interesting question is then that means when I'm optimizing for theta, the first term is redundant. I need not use it. Okay. So P and Q means P is P theta and Q is P theta. Okay. Not necessarily like that. It has converged means it has nothing as lost. In fact, the best result is when discriminator gives 0.5. 0.5 means what? It is not able to tell it is this class or that class. It is confused, chance. So the best case is when your discriminator will go to 0.5. So that's the best case. That means discriminator is totally confused now. Yeah. That's mode collapse. That is mode collapse. What you said. So yeah. So that's where it happens. Yeah. And that is the most common problem in the GAN type of model. When you are going to the forward KL, where we are going to the forward KL? Previous cases. Because so it happens because what happens is that sometimes you have data, most of the data from one mode, and other mode has very few data. So then during training, it gives very less weightage to those, ignores those almost. So it learns only one of the modes. So it thinks instead of a bimodal Gaussian, it is having a single mode. So in that case. Okay. So I'll repeat once more. This is known as GAN. I did not write it, I should write it. So this is GAN. GAN stands for Generative Adversarial Network. Yeah, and it is actually very good, but then there are issues such as mode collapse and all of those things. So the advantage is likelihood free. So that means you can take decision based on samples only. No need to. Disadvantage is unstable training. Whatever other problems are there are emerging from this. There are tricks to nullify this unstable training, but you might not succeed, or it might take huge time for you to succeed. Okay. Yes. Yes. Samples. It is taking these and training is based on samples, no likelihood evaluation, right? Okay. So now, in the remaining 10 minutes, let us look into some mathematical aspects of GAN. Okay. some mathematical properties of GAN. Properties. I'm still deciding whether I should prove it or just write it, but that's okay, I think. So first one is optimal discriminator. So can you tell me what is the optimal discriminator by looking into this prop expression? What is the optimal discriminator? Optimal discriminator means if I take derivative with respect to the discriminator, that should be equal to 0. That's what it means. So what is the optimal discriminator? It's a variational thing, but anyways. You have to look there to get the answer. Looking here will not give you the answer. So you look there. So how will you find the optimal? Its expectation. Just write in terms of integration. Okay. And then you will take derivative of that. Now this integration is actually evaluated pointwise. That means you can ignore the integration and take whatever is inside the integration. Take derivative of that, equate it to 0, you will get. Okay. Because what will you get? If you take integration, what will you get? Integration of log d phi multiplied by p theta dx plus integration of log p theta, not log p theta, p theta x log 1 minus d phi x dx. You can write these two integration together. So it will be a single integral, integration of p data multiplied by log phi, log d phi plus 1 minus, or no, not 1 minus, let's not write 1 minus, p phi, p theta multiplied by log of 1 minus d phi dx equal to whatever. Now take derivative of what is inside with respect to d. So first term is what? P data multiplied by log of d phi. Derivative with respect to d phi. It will be p data divided by d phi. The second term is what? 1 minus p phi divided by 1 minus d phi, and then a minus sign will come in because of the 1 minus thing, and this should be equal to 0. And now you do a cross multiplication, find out d phi, you will get it to be equal to p data divided by p data plus p phi. Okay, you can do it. This is exactly what you will get. Okay. So optimal one you will get as d phi star is equal to p data by p data plus p theta. Hmm? Exactly. That's optimal one. Right? So that will happen only when theta will reach to theta, right? What is the best? What is the optimal p theta? P theta. When p theta is p theta, what happens to this? Half. I told you that it will get confused if it becomes best, right? So you can also validate it from there that the best theta you can have is p theta. If p theta is equal to p theta, you are getting 0.5. So when you have the best generator, the discriminator do not know what to do, right? Independent of what you are giving. Okay. Now what is the likelihood, log likelihood, let's call it, when your discriminator is optimized? What is the likelihood when because likelihood is what you are maximizing, minimizing, right? So that's why I'm focusing on that. What is the likelihood when discriminator is maximized? Go back to here again. So wherever there is d phi, you will put p data upon p phi, right? Now p data plus p phi is actually not a normalized distribution. A normalized distribution is p data plus p phi by 2. You can check it. I mean, integrate to 1, so that's how we get it. Okay, because p data itself will give you 1, p phi itself will give you 1 if you integrate them. So by 2 will actually be a normalized distribution. Okay, because for being a valid distribution, integration should be equal to 1. That's the basic case, right? So if you put, anyways, that is needed later, but let's put p theta, p theta by p theta plus p phi, p theta. What will you get in these two cases? In terms of KL divergence, think. It's a KL divergence. What will you get? What will be the first term? Someone tell me. Do it and tell me. I will not do it. I want you to do it. So what you are doing is, instead of d phi, you are putting p theta divided by p theta plus p theta. That's what all you are doing. Now do it. And if you want normalized, divide by 2 and multiply by 2. Log 2 and log 2 will come outside, so it will be minus log 4. If you want, you can do that. Expectation of log 4 is log 4, so that's why. So that log 4 you can take outside, but the remaining part, what will happen? KL divergence formula, I hope you remember. Expectation of log p by q, right? So just focus on the first term and tell me what it will be. This is the last thing, so you can see I'm wrapping up things, but I want you to do it. Remember the expectation that p here is p theta, by the way, and q is p theta. So keep that in mind. It will be needed. When I'm writing expectation x belongs to p, that is p theta. And when I'm writing expectation x belongs to q, that is p theta. So keep that in mind. Otherwise, you will not be able to do. It's not that difficult actually. You should be able to tell me. It's actually very simple. Scale dimension of p theta with respect to by 2. When I said by 2, you do. So yeah, you're right. The first term will be KL divergence between p theta and p theta plus p theta by 2, because I told you to that do it by 2. Correct? What is the second one? Now you should be able to tell it just by seeing it. You should not be needed. You do not need to now do the calculation. Right? They are opposite actually, to look into. The second term remains the same. The first term, in one case it is p theta, the other case it is p theta. Right? These two terms together is twice the Jensen-Shannon divergence. This is a type of divergence also. It is also known as symmetric KL divergence. It is symmetric. If you put theta and if you switch the two things, it will remain the same. So this is known as Jensen-Shannon divergence times 2. So what you are getting is 2 times Jensen-Shannon divergence minus log 4. That's what you are getting. Because you are getting one KL divergence between p theta and p theta plus p theta by 2. The other KL divergence is between p theta and p theta plus p theta by 2, and minus log 4 you are getting because by 2 I asked you to do. So if you remove the log 4 term, minus log 4 term, the remaining two terms, that is 2 times Jensen-Shannon divergence, which is also known as the symmetric KL divergence. Okay. And now you can see that the optimal loss, if you put this, optimal loss will be 1. When each of these will be equal to 0, right? which is when p theta is equal to p theta. And at that time, this one will come out to be minus log 4. Because the two KL derivatives will go to 0, and what you will get is minus log 4. Right? This is a small mathematical exercise. I mean, maybe not that important, so I did not write it, but you can derive it easily. Okay. So it's like 2 line, right? Why normalized? Because otherwise it's not a valid distribution. What is the definition of a PDF? Integration should be equal to, so it is not 1. Then it's not a PDF. So then, right? Okay, I'll see that one. Okay, so tomorrow we are meeting at 8:30 for the exam. Okay, which I'll set the question now. Okay, thank you.